Hi, this is Introductory Econometrics. Topic, Ordinary Least Squares, OLS approach. Consider a two-variable sample linear regression model. Y is equal to beta 1 at plus beta 2 at x plus u at. Let's call this equation 1. OLS approach finds the beta 1 at and beta 2 at, which minimize the residual sum of squares. That is RSS, summation u at square in equation 1. That is, this RSS is the summation u at square in equation 1. So when we solve this u at, we sum the square of this r at throughout the observation. So we arrive at RSS, that is residual sum of squares. So we sum the u at square across the observation. So when we do that, we are going to have residual sum of square, that is RSS. So now let's show how to derive the OLS estimators, that is beta 1 at and beta 2 at. So step 1, make u at the subject of the formula in equation 1. That is, this u at in equation 1, we have to make it the subject of formula. So if we try to do that, so we are going to have this expression, u at is equals to y minus beta 1 at minus beta 2 at x. So we can put in brackets. So step 2, squaring both sides. So when we square both sides, we are going to have u at square is equals to, in brackets, y minus beta 1 at minus beta 2 at x. We square, we close the bracket and we square everything in the bracket. So that will make us to have u at square. So step 3, we sum both sides. So when we sum both sides, we are going to have this expression. Summation u at square is equal to summation into bracket y minus beta 1 at minus beta 2 at x. We close the bracket and we square. So by this, we'll be able to achieve RSS. That is, this is known as RSS. That is summation u at square is equals to summation into bracket y minus beta 1 at minus beta 2 at x. We close the bracket, we square the expression. So this expression, okay, implies residual sum of square. That is, since RSS is the same thing as summation u at square, so we can simply replace this summation u at square by RSS. That is, RSS is equals to summation into bracket y minus beta 1 at minus beta 2 at x. We close the bracket and we square it. So you recall that we said OLS approach finds the beta 1 at and beta 2 at, which minimize the residual sum of squares, that is RSS. So we have been able to derive residual sum of squares, which is this expression. So the next thing is to minimize this expression and set to 0. By doing so, we'll be able to find beta 1 at and beta 2 at, which minimize this residual sum of squares. So step 4, minimize RSS, that is the residual sum of square, and set to 0. That is, we have to find the partial derivative of RSS, that is of this expression, with respect to beta 1 at, and we set it to 0. And we also find this, the partial derivative of RSS with respect to beta 2 at, and set it to 0. So this represents the first order condition of this expression with respect to beta 1 at. and we set this first order condition to 0. And this is the second, this is also this first order condition of this expression, that is RSS with respect to beta 2 hat, and we also set to 0. So next, so we want to find the derivative of RSS with respect to beta 1 hat. So this is the expression we have to differentiate with respect to beta 1 hat and beta 2 hat, and we set each of these to 0. So when we differentiate RSS, that is, we find a partial derivative of RSS with respect to beta 1 hat. So we have this expression. So we bring down the power here. So we have 2 summation into bracket y minus beta 1 hat minus beta 2 hat x. We close the bracket. So since we are dealing with chain function, so after differentiating the whole expression, okay, so we still need to differentiate what we have in the bracket. Since our focus is beta 1 hat, so when we differentiate this, okay, that is, we differentiate this with respect to this beta 1 hat, that is minus beta 1 hat, so we are going to have minus 1. That is, this, the partial derivative of RS set with respect to beta 1 hat in this bracket, okay, it gives us minus 1. So that's why we have multiply. This dot means multiply by minus 1. So don't forget, we have to set this expression to 0. So look at this next line. So we multiply this minus 1 by this 2 before the summation. So by the time we do that, we are going to have minus 2 summation into bracket. We are going to have this whole expression there. That is y minus beta 1 hat minus beta 2 hat x. We close the bracket is equal to this 0, equal to 0. Next thing is to divide both sides by minus 2. Since what we have here is a constant, so we can simply divide this whole expression and this side, that is, with divide both sides by minus 2. So by the time we divide both sides by minus 2, so this 2 will go away, and 0 divided by minus 2 remains 0. So hence we have this, that is summation into bracket y minus beta 1 hat minus beta 2 hat x. We close the bracket is equal to 0 divided by minus 2 gives 0. So we could call this one equation 2. So we do the same thing for beta 2 hat. That is, we find the partial derivative of RSS with respect to beta 2 hat. That's what we have here. So when we do that, we are going to have this. So we apply the same method, the same rule. This is a chain function. We bring down the power. So we are going to have 2 summation into bracket y minus beta 1 hat minus beta 2 hat x. We close the bracket. So chain rules say that we are also to differentiate what they have in the bracket apart from the whole expression with respect to the variable or the parameter we are interested in. So when we differentiate this with respect to beta 2 in this expression, the expression in this bracket, so we are going to have, we have minus beta 2x. By the time we differentiate with respect to beta 2 here, so we are going to have minus x. So that is why we have multiplied by minus x here. Don't forget, it's equal to 0. We have to set to 0. So here, this minus here, we multiply it by this 2 here. So we have minus 2 summation into bracket y minus beta 1 hat minus beta 2 hat x. We close the bracket and we have x left here. So we put it there after the bracket is equal to 0. So next thing is to divide both sides by minus 2 because this is a constant. So we divide by minus 2. So we have summation into bracket y minus beta 1 hat minus beta 2 hat x. We close the bracket and we have this x1, we have this x outside the bracket equal to 0. So we call this equation 3. So next thing, we open this bracket, okay? We open this bracket. So because we have to solve these 2 equations, that is equation 2 and equation 3 simultaneously in order to derive our beta 1 hat and beta 2 hat. okay, that minimizes RSS. So we open the bracket in equation 2. Here, this is equation 2. So we open this bracket. That is by multiplying this summation by each of the component in this bracket. So when we multiply that, we say, so this summation multiplied by y. So that will give us summation y minus this summation multiplied by beta 1 hat. Since here, beta 1 hat is a constant, okay? It's not a variable, it's a constant. So when summation is multiplied by a constant, that summation changes to n. That is changes what? The number of observations we have, okay? So we have, that's why we have minus n beta 1 hat. So we cannot have summation beta 1 hat. So that summation we change to n beta 1 hat minus here we also multiply this by this. But since we have a variable here, so we can put this summation at the back of this beta 2 hat so that we have beta 2 hat summation x here is equal to this 0 here. Okay. Next thing is to make beta 1 the subject of the formula. So when we make beta 1 the subject of the formula, so we have n, the first thing to do, we try to rearrange our expression here. So we have n beta 1 hat is equal to summation y minus beta 2 hat summation x. So next thing is to divide both sides by n. So when we divide both sides by n, so we are going to have this expression, okay? The expression beta 1 hat is equal to summation y minus beta 2 hat summation x, everything divided by n. So when we divide this by n, we also divide this by n. So since summation y divided by n is equal to y bar, that is the main of y, that's the main of variable y, and also summation x divided by n, that is the number of observation. So also implies x bar, that is the main of variable x. So we can say that beta 1 hat is equal to y bar minus beta 2 at x bar. So this is the formula for calculating beta 1 hat, and this represents beta 1 hat that minimizes the residual sum of squares. So also we need to calculate the formula for calculating beta 2 hat. That is, we also need to find beta 2 hat which minimizes the residual sum of squares. So we go back to this, our equation 3 here, okay, because this is where we differentiate our residual sum of square with respect to beta 2 hat. And this is the last expression here. We name it equation 3. So this equation, so we are going to use that equation to derive our beta 2 hat. Okay, so when we do that, look at the equation here. This is the same equation we have in equation 3. So next thing, we try to multiply this x outside here by each of the component in this bracket. So that is what we have in this expression. So we have x multiplied by y. So we have x, y. So minus x multiplied by beta 1 hat. So we are going to have beta 1 hat x minus x multiplied by beta 2 at x. So we are going to have beta 2x squared. So we close the bracket is equal to 0. So the next thing is to open the bracket. So what we mean by opening the bracket is that we are going to multiply this sum outside by each of the component in this bracket. So we have, by the time we multiply this summation by xy, so we are going to have summation xy minus, we have a variable here, so we are going to multiply this by that variable. So we have beta 1 hat, which is here, this multiplied by this, so we are going to have summation x minus, so we also have this sum multiplied by this, so we are going to have this constant outside here. Okay, so we have beta 2 hat, and we have this sum multiplied by x squared. So we are going to have summation x squared. So equals to this 0. Okay. So the next thing is to substitute equation 4, that is this our beta 1. So we have to substitute this beta 1 expression, or this beta 1 formula, equation 4, into this our equation 5. Okay, so that is what is written here. Substitute equation 4 into equation 5. Okay, wherever we see beta 1 in this equation, so we are going to write this bar y minus beta 2 at bar x. That's what we are going to write. So that is what is done here. So we have this component, we have summation x, y, okay? This minus is it. So here, let's first write this expression, okay? So this expression, this is it. So we have this summation x here, and this is beta 1. So you recall that in equation 4, here, our beta 1 is this, y bar minus beta 2 at x bar. So we are to write it here. So this replaces our beta 1 at minus, this minus is here. So we have beta 2 at summation, this summation x squared is equal to 0. Okay, so next thing is to open this bracket. So we write this. So we have this, we write it here, that's summation xy, and this summation xy, minus this minus here, and we have this. We have to open the bracket, so we multiply this summation x by y, or y bar. So we have y bar summation x, y bar summation x, when we multiply this by this, okay? This minus times minus, that is plus. So we have this summation x multiplied by beta 2 at x bar. So we have this beta 2 at, we have this x bar, and we have multiplied by this, we have summation x, and minus this minus, that is what is written here. So we have beta 2 at summation x squared is equals to 0. Okay, so since summation x, this summation x over n is equal to x bar, so we can say that n x bar is equal to summation x. How do you get that? When we cross multiply, so we are going to get this times this, that's x bar times n, so it gives us this. Since it is 1 that is here, so 1 times this, we are going to have summation x. Okay, so detail for this y bar too. Okay, but this is what we want to use in this expression. So meaning that wherever we see summation x in this expression, okay, we are going to replace it with nx bar. So that is what is done in this expression here in this line. So we still have this summation xy. This is it, minus this. So now we have this summation x. So wherever you see this summation x, don't forget we have to replace it with what? Nx bar. That is what we have here. So this y bar is here, and this summation x, that is what we have, this nx bar that we have here. This nx bar, that is summation x we have here, and this y bar, that is what we have here. So plus, this plus is this. So we have this beta 2 at, this is it. And here we have x bar, that is x bar. Don't forget, we also have summation x here, and that summation x here is nx bar. So meaning that we are going to have nx bar, x bar. So x bar multiplied by nx bar, we are going to have x bar squared. So don't forget, we have n here, okay? N x bar multiplied by x bar. Look at this component. Here we have x bar, and this is nx bar. So x bar multiplied by x bar. So we are going to have x bar squared. And we also have n beside. So that is n here. We now have this component is equivalent to this component if we use this to replace this. So minus, look at this minus, beta 2 at summation x squared is equals to 0. So next thing is to rearrange this equation. So we want to bring this to this side and this to this side, okay, in order to make it easier for times collection. So we have this summation xy minus n. So this n is here, so we just wrote it here. So we have this y bar and we have this x bar. This and this are the same thing, okay? Okay, this and this are the same thing. So here we have this, we are writing this first. So we have minus beta 2 at summation x squared. That is what is written here. That is minus beta 2 at summation x squared plus this one, beta 2 at n x bar squared is equal to 0. So now, since we have beta 2 at here and we also have beta 2 at here, so we can factor beta 2 at out. So here we have this expression. So we have summation xy, which is the same thing as this summation xy, minus this n y bar x bar. You can see we have it the n y bar x bar, minus this beta 2 at, we factor it out. So we have summation x squared left here. So this sign will change to minus so that when we multiply this, we open this bracket, we are going to arrive at this plus. So we have minus, we are left with n x bar squared here. So that when we multiply this, so we get back to this expression. So it's equal to 0. So next thing is to collect the like times. We want to collect the like times. So we take this part of the expression to this side, and this remains on this side. So we have this same expression here. So we have summation xy minus n y bar x bar is equals to, we take this to this side. So we have beta 2 at into bracket summation x squared minus n x bar squared. We close the bracket. So the next thing, since our aim is to derive beta 2 at, so we make beta 2 at a formula. So how do we do that? We divide both sides by the expression beside this beta 2 at. Then we divide both sides by summation x squared minus n x bar squared. Okay, so this is the expression. You can see that we have summation x here. So it should be summation x squared. So this expression, summation x squared minus n x bar squared. So we divide by this expression. So that's what is done here. So this, when we divide this expression by this, so we have beta 2 at. So this component, that's summation xy minus n y bar x bar divided by this part, that is summation x squared minus n x bar squared. So it's equal to beta 2 at. So we can rewrite this as beta 2 at is equal to summation xy minus n y bar x bar divided by summation x squared minus n x bar squared. So this represents beta 2 at that minimizes residual sum of squares. So this is the derivation of OLS estimators. So here we can also prove that this expression, that is the formula for calculating this beta 2 at the OLS estimator, this formula for calculating this OLS estimator beta 2 hat is equivalent to this expression here. We also prove that this beta 1 hat, which equals to this, is also equals to this, is equivalent to this one. We can also prove that. That will be the subject of our next class. Thank you very much.